All right.
See if it wants to work. Cool. So welcome everyone. I think this is our third workshop in Developer DAO. So far we've had welcome everyone. We've had Strider think about. Had it playing in the background, didn't I? So yeah, sorry again. Welcome everyone. I think this is our third workshop now in Developer DAO. We had our first was on security from Strider, kind of like personal OPSEC. If you haven't seen that, go check it out. Lots of actionable, useful information for keeping yourself safe in crypto and Web3. Second was from Developer DAO OG Daiwa, talking about how to permanently deploy React apps onto Arweave, which was really, really good as well. Definitely go check that out if you haven't seen it today. And all of this has really been made possible by Ropats, kind of getting all of this stuff on the ground. So if you haven't given them any...
Maske da? Eine Maske zu kaufen?
One sec. Ropats. Okay, don't worry. Yeah, cool. Sorry, all of that's been made possible by Ropats. So if no one's given him, if you haven't given him any kudos yet, make sure to hit him up and say thank you. But today we are very, very lucky to have Andreas with us. How are you doing, Andreas?
I'm good. How are you guys?
I'm doing very, very well. I'm just trying to find the person who is unmuted to see if I can mute them.
The culprit is repo level D.
Okay.
Oh, he's muted now.
yeah, I've done it. It's cool. Yeah, good man. Thank you. So yeah, really, really appreciate you coming up to do this. This is certainly a rabbit hole that I haven't really gone down yet. So I'm interested to see kind of where it goes. Everyone should be able to see Andreas is going to be speaking about Ethereum as a sort of decentralized world database and how it handles data. So Andreas, mate, welcome. If you want to kind of introduce yourself and then kind of roll onto what you'll be covering today, that would be amazing, mate.
Hi guys. Well, keep it short and sweet. I'm very much like many of you. I'm a sort of a newbie in the blockchain space, and I'm learning and taking the opportunity in the DAO to kind of pay it forward and do a little bit of educating at the same time. So that's all you really need to know about me at this point. And I'm just gonna get straight into it, guys. I'm just gonna be showing you stuff on my screen. The repo will be available. This is part one of a two-part workshop. This part is gonna be kind of more theoretical, and then the second part we will take whatever we cover in this workshop, and we're gonna apply it to kind of more real-world scenarios on the Ethereum blockchain, like authenticating and improving a route of a transaction tree, or a transaction route that we find in a block, or the receipt route that we'll find in the block, and also we'll delve into the storage tree, which in itself is like very interesting, and hopefully there'll be some insights in there. So all right, let's just get into it. Let's get into it. As Anthony Sassano would say.
Okay. And Andreas, dude, just before you go, you're quite happy to take questions as you go, right? If people want to sort of jump 100%. In and ask.
100%. Anyone at any point has a question, it's better if they just ask it immediately. There's no problem with cutting off the flow and everything. Just jump in and whatever the question is. Like, don't just just ask it.
Cool. And if you don't want to speak, I'll keep an eye on the chat and I'll nudge you, mate, if there's any questions coming in.
I'm only gonna be looking at VS Code and Chrome. So please, if you could do that for me, if that's okay, because I'll try, but I doubt I'll be able to look back that much. People can just kind of shout in if they want. People can unmute and just stop me if they want. All right, so just quickly to get into it. So basically, I've been down the rabbit hole for the past 2.5 months, and I'm gonna show you to the best of my ability from end to end what it means to take data that you would put into a transaction, and how that data is then transformed, encoded and whatnot, and how it finds its way into a database which is secured by the security of the blockchain, basically. So first of all, just quickly, just so you can have this kind of little picture in your mind. Obviously, all data is part of the blockchain, but some data, which is basically on either like which is, say, for instance, predominantly on a LevelDB database, doesn't actually sit on the on the blockchain. It's just data that can be authenticated as being part of the blockchain, right?
And
So
Andreas,
basic. So hello.
hello, man. Can you zoom in just a little bit on the browser window? There you go. That's perfect, dude. Love it.
Okay. Let me just do the same. Do I have to go this big in VS Code, or can I stay at this level?
I think you'll be okay, but I'll nudge you, mate, if anyone says. Don't worry.
All right, no worries. Okay, so basically, this is all in the repo that I will be posting. It's already up. I'll link to it. Um, basically, these are specifically the three sections that we're going to talk about now. Is we're going to talk about RLP encoding. We're going to do we're going to discuss what tries are, tries, depending. I'm not sure how you're supposed to pronounce it, as a sort of abstraction, and then we're going to talk about the Merkle Patricia trie, and how the Merkle Patricia trie is used as an interface to a LevelDB database, or a RocksDB database, which RocksDB is actually based. It's like a fork off of LevelDB, and so we're gonna go end to end, from information that might be human readable all the way to how it looks on a database and how it's retrievable. We're gonna be using the RLP library, but from Ethereum.js. We're going to be using Ethereum.js trie library. We're going to be using the level library, which is like the JavaScript level DB library. Uh, Ethereum transaction, actually not in this session. Neither hard hat, and Ethereum.js, basically. So before we dive into stuff, I'm gonna quickly just talk about some kind of concepts. I'm gonna do a concept review, because this is stuff that we're gonna continuously keep seeing over and over again in the code. Okay, so the first thing that you're gonna have to remember in kind of the back of your head is hexadecimal to decimal conversion, right? Like decimal numbers to decimals, and very importantly, as expressed as bytes. Obviously, I've just kind of like left a couple of JavaScript ways that you can bounce back and forth between decimals and hex values, just as a little refresher. um then we have to keep in mind the concept of nibbles, because like as half a byte, uh we will see that later on as well. And nibbles being hex values from 0 to f, or 0 to 15 expressed in decimal format. Okay, then expressing bytes, we will encounter bytes expressed in different ways within the different libraries. A lot of it's going to be in Node.js. So if you're familiar with like the buffer object in Node.js, we'll see the buffer object, and we'll see bytes expressed in hex. And the different ways that you can actually produce that buffer, by passing sort of hex values as a string, or numbers. uh we will see the native JavaScript uint8 array, which is expressed in this format when you see it in the console. And you have to I'm sure you guys have toyed with these, but effectively, whenever we see these values, they're always going to be expressing the same thing. But most likely they'll either be expressing it in hex, or they'll be expressing it in decimal. Then the last one more concept is the concept of a data hex. which is basically a string representation of a byte, which is always like it's an even number of nibbles, right? So as a data hex being even number of nibbles rather than an odd number of nibbles, which is more problematic to express as bytes. And just as a quick reminder, 0x as a string is a valid value. It represents an empty byte of information, all right? So, and then one last thing, and this is actually quite important. It will see it a lot in everything that we're doing from here on out, and that's the concept of recursion in programming, right? So basically, recursion being functions that will call themselves internally, right? And this is like a very powerful pattern, and it allows us to create it allows us to create sort of like nested objects. So this function over here, when run, will create a nested object of like this. uh, we don't have to go over the code or anything like that. Or alternatively, like the same kind of recursive function can be used in such a way that you can take an already nested object. So in this case, this array with arrays nested inside it that have other arrays nested inside it, and interpret that. Use the recursive function to interpret that as a sort of serialized string, which I didn't actually do. I didn't create this, but one of you could have a shot at it. But it is to basically create another recursive function that would read linearly through this type of string and then rebuild the nested structure that it originated from. And like these two concepts, this structure and this structure represented as a serialized version like this, we are going to immediately start seeing a lot. Okay, so all right, that's the introduction. So let's just jump straight into one of the branches, the RLP branch. Okay.
Andreas,
Yes.
do you want people to be following along? Have you got a links that you would want people?
I would rather people follow along on the screen, and if someone thinks I'm going too fast or I'm not pointing to things, to just call it out and ask for something to be explained.
Got it, man. Cool.
Yeah, because just because it'll be easy. I hope it will be easier if they just follow along with me.
Sounds good, dude.
All right. So okay. So RLP. I'm gonna read you this information because it's a mouthful, and all the stuff that I'm gonna read to you now. Don't worry if you don't understand it immediately. We're gonna practically look at it as well. Okay. All right. So RLP encoding and decoding, which stands for Recursive Length Prefix, is a custom Ethereum encoding system that accepts nested structures and expresses them in a series of bytes that can be decoded back into their original structure. Okay, so like this down here. This is an example. This is an example of like a nested structure that has been RLP encoded into this serialized string, right? RLP only recognizes two types of items, in quotations items. A byte string, which a byte string means a series of bytes, which is of length 1 or more. So this is like a byte string of 3. This is a byte string of 1. And a list, which effectively a list is an array. It's just an array. And the array is any combination of byte strings or lists or list, right? That's the sort of recursive element inside like the encoding and decoding of RLP. RLP is agnostic of the data you encode. It has it has no knowledge of the content. It is up to the consumer of the decoded content to interpret it, and I will explain that as we go along. It prefixes items with a byte or multiple bytes that describe the item and its length. hence length prefix, right? That's the length prefix in the name. It is recursive in that lists can contain lists, and every depth itself is encoded. When encoding parent items, the length prefix of the parent will take into account the length prefix bytes of the child when calculating its own prefix. Again, we're gonna see that in practice, okay? So don't worry if that didn't just like completely connect. So yeah, again, this is an actual this is an RLP encoded version of this structure right here with this array of arrays with a byte with multiple byte strings and all that stuff. So RLP encoding is 6 rules, and when I tell you them now, they may seem a little complicated, but they are actually extremely simple. Okay, so just one way that you can think about the rules is they're separated in 2 rules for single byte values, uh, 2 rules for multiple byte values, which is the byte string idea, and 2 rules for list values, which is like the array, right? Okay, so rule 1: a single byte whose value is in the ASCII range does not require a length prefix. We're just gonna leave that at that, and I'll explain it in detail as we go along. Rule 2: empty values are encoded as the byte 80 in hex, right? So the hex value 80. So examples, actually, don't forget null. This is null solidity and all that stuff. Like null really isn't a concept. Just think of it as just empty information. So an empty string or an empty byte value, and you'll see how empty byte values come into play as we go along. The value 0 is not an empty value. The multiple byte rules, rule 3 and 4: to encode a byte string of length less than or equal to 55, like so a byte string which has 55 bytes in it or less, we start from the hex value 80 and add the length of the byte string. You may encounter this rule expressed as this. I mean, I will also include, I haven't finished this yet, but I'll include a whole bunch of links to articles, and you will see that expressed in this format, which basically means the byte string, then the length of the byte string, and which is added to this first value of 80. To encode rule 4: to encode a byte string that's greater than 55, we take the length of the byte string, right? So this is the string. We take the length of the byte string, then we we add the length of the byte string to the first prefix value and concatenate it all together. We're gonna put all this stuff in practice. So the array rules, the exact same rules that apply to the byte string rules, except that the initial prefix value is different, right? So if it's less than or equal to 55 bytes in length, we apply the rule 0 oxc0 as an initial value plus the length of the list, followed by the list, right? The one thing to take into consideration here and to remember is that concept of like recursion. So basically the items inside the list could very well be byte strings, right? And like they will also include their own bytes of information, which are like like the prefix that was added to them, and those bytes will also be taken into consideration when it comes to the length. And then rule 6 is again the same as the byte string longer than 55. We do this kind of like the length of list added to the prefix f7. Okay, if you come back and read this, just so you know, there's a couple of functions that I added here which will help you sort of like do some calculations if you're kind of having some troubles with the with the encoded values. Like these functions can help you like calculate those, but I'll let you dig into those alone. Okay, so when decoding bytes, so like these are the range of bytes that each individual rule set contains. And so basically rule 1 is from 0 to 7f. It's 128 possible bytes. Rule 2 is only one value, the value 80. Rule 3 is 81 to b7, 55 possible bytes, and so on and so forth, right? Like no need to go through all of them. So the again, to just emphasize the idea of that RLP encoding is an agnostic form, is agnostic of the information that you embed in it. It is both used when you RLP encode transactions, and these are the signatures that you would use for RLP encoding different transaction types, and they have to be in the specific order because whatever consumes that RLP encoded information has to have its own rule set to know how to interpret like the data that it decodes, right? So same with receipts, and then as we're gonna see in a little bit, trie structures as well are are RLP encoded using like what obviously look like very different structures than the above structures, and this is just to at this point drive home the concept that RLP doesn't know what it's encoding. It's just whatever is consuming that information that needs to know the rules of the decoded information. Oof. Okay, that was all. That was all the explanation about RLP. So now we're gonna go through the RLP rules one by one, and then we're gonna move on to other stuff. All right. So quick. It can is screen size okay at this point? Like is everything okay?
Maybe do one more, mate.
Oh man, that's getting tiny. Okay, so just really quickly, I just want to like point out like there's two different libraries that you can use for RLP encoding. One is built into Ethers, the other one is provided by ethereumjs, and while they both follow the same RLP encoding rules, they differ. The two ways they differ is that ethereumjs will give you back the encoded output as a uint8 array, like a JavaScript uint8 array, while ethersjs will provide it as a data hex value, right? Like a string of OX prefix kind of numbers. Generally speaking, the ethereumjs's implementation is more of a Swiss Army knife. It will allow you to provide more values into it, and it will format them internally into what is necessary. So you can pass like a number, and it will decide that that's just a byte. That's a byte as a uint8 array, and it will encode it for you. You can pass a hex prefix string. You can pass a uint8 formatted array. You can pass a buffer object from Node.js. You can pass an array, and it will assume it's a uint8 array. Pass an array of hex prefix values, and it also has these two convenience functionalities, which is one of them is that it will normally you shouldn't be playing and messing with like bytes that are presented in just with one nibble. It will kind of make the assumption for you, and it will just pad it with a 0, and that's sort of a convenience functionality, but you shouldn't rely on this. The other really interesting one is it will transform text into what needs to be RLP encoded. Like it will transform it to ASCII, and we're going to see that now with rule 1. Like ethersjs will do a lot of the same things, but it will provide errors on things like trying to pass numbers, trying to pass just an array. It doesn't like just odd nibble hex values. And this is kind of a nice little failsafe because that can cause errors sometimes. but so you just can't do it, and it will not do any formatting for you on text. You would have to do this externally and then pass it for it to be encoded. All right, so let's go. Rule one. Let's look at this stuff kind of let's look at this stuff, and I promise you as we go along, this stuff is going to become more useful. Okay, so rule number one, the hex values 0 through 7f, which are also in decimal the values 0 through 127, which are deliberately, right? They're deliberately the ASCII values. So I'm just going to show you, the ASCII table real quick. And it's basically all the kind of normal things that you would type on a keyboard, and how a computer it understands them, right? It understands them as the decimal values, or these hex values, right? So rule one is the quirkiest, the weirdest of them all, because the rule is about a single byte of information. And it's basically saying, if I encounter a single byte, a string which only has one byte, and it falls within this sort of like ASCII range, I'm not gonna put a length prefix in front of it. Okay, so just to quickly show you in Node. Oh man, I hope this is working. So I'm just gonna RLP encode the letter A for you using ethereumjs implementation. What happened here? Okay, excuse me while I just basically close this and just do it manually. Can you? I know this isn't ideal, but okay. Equals require RLP. Okay, so that first value A, right? And remember, this is a convenience method offered by ethereumjs. So it encoded it to the value 97. If you look on the ASCII table, right, where is it? 97 is the value A, right? So why is this strange? The reason that it's strange is that it's not entirely clear why you would ever care about this one value. If I was to, for instance, right, I'm taking this string that says hello, and I'm going to basically turn it into an array of the ASCII values. So if I just print that, you can see down here, this is the array that represents the word hello in ASCII. If I then take that array and just turn it into what is referred to as a byte string within sort of like RLP. If I take that, like, you'll see that the ASCII byte string, right? It's converted to a uint array. If I RLP encode that, it now has gotten, you'll see that there's one extra sort of byte of decimal information in front of it, which would be the equivalent of if I encoded values that were higher than that value. So AA, BB, CC, DD, EE, they all are higher than the value 7F, right? You can see that they both got an extra prefix to them, which we will explain like later on. It's an odd rule. The only reason I could think that the rule exists is if you were to try to encode like individual ASCII values as an array. You will see here like C5. We'll get to it. This is part of like rule 5. Like, you can see that there's no other encoding in between. But if I was to do the same with values that are outside of the range, now you can see that each one individually has received some like a length prefix, right? So okay, that's rule one. It's gonna get quicker as we go along, guys, and more interesting. So just hang in there, hang in there. Rule two. Rule two, like really simple. Anything which is empty gets expressed as the value 80, right? As the hex value 80. So if I was to basically RLP encode a uint array, like a new one with nothing in it, it comes out as uint array 128. Which if I and from here on out, I will continue to do this, but I will do it. I'll show it in sort of like in hex values. You get the value 80, right? So 128 in decimal equates to the value 80. And everything in this list that you see over here, like whether creating an empty buffer, whether passing the string OX, which represents the value 80, that gets encoded to the value 80. Empty string, the same. What doesn't is the value 0, right? That gets covered. This is actually covered by rule 1 that we just went over. So what happens if you want to actually encode the value 80 itself, right? Like what if you want to encode the value 80, since the value 80 is already taken up, it's kind of like a reserved value. Now we've come into rule 3. We're like rule, so okay, it's like you can already see if you're kind of following the logic, we know that the value 128 is 80 in hex, 129 is going to be the value 81, okay? So, and this now this is like this is moved this into rule 3, which the rule was is if a string is if a byte string is from one, if a byte string is from one value which is higher than the ASCII range, or any other number of values 2 to 55, apply this rule, right? So basically 128, like what we just did, that value is a decimal, which is the value 80 in hex. If RLP encoded return, all right, let's just do it. Actually, yeah, buffer from, did I already do that? I don't know if I did. 8180, and this is the first time now we're looking at this kind of like length, in quotations, length prefix part of the encoding, right? So we started with a value 80. We see that our string of bytes is only 1 byte long. We add it to the value 80, and we end up with a value 81, right? So I won't go over all these examples, like but just keep in mind, like you can actually do some interesting stuff with this encoding. Like you could, if you wanted to, you could encode code itself. You could upload code, like JavaScript code or a stringified object, into a transaction RLP encoded, and as long as you before you encode it, you turn every single character into its ASCII value. You can encode it onto the blockchain, and I think that's also very much part of how, you know how sometimes you see transactions on Ethereum which have a message, they have a message as the data. It's kind of connected to this reason that RLP encodes that ASCII range. So from here on now, I'm gonna use a like a function that creates like a random bytes of a certain length. Okay, so that we can see all the rest of it in fast forward. All right. So for instance, if I was gonna encode a string of like a series of bytes that had 10, a string of 10 bytes, right? You can see right here the prefix is 8a. A in hex representing the number 10. So that was added to 80. So this is basically saying, in a linear way, it's saying like it encounters it encounters this this byte and it says, okay, after me, this byte string has 10 individual bytes in it, right? So I'm gonna do the same with 55. Oh, I'm gonna do the same with 55 real quick. All right, this is our string of bytes, and we can see like the length prefix is the value B7, which is the final value that is allowed in this rule. Okay, so moving on to rule 4. Okay, we just saw what a 55 length byte looks like. So let's look at a 56 length byte. All right, so now we're in B8. B8 being the first, it's the first value in the range of it's the first value in the range of the rule range of hex prefixes. Okay, but okay, so I just encoded the value 56. Let's look at what the length of the RLP encoded byte string is once it has been RLP encoded, right? So it's gonna internally RLP encode it. It's gonna convert it to a Node.js buffer, and then we're gonna read its length. Okay, 58. So we added. I hope you guys can follow my my cursor. We added the value 56 in it, but the final value is 58. All right, the RLP encoded value is 58, which brings us to that really strange rule, right? Which basically we know since it's 58, we've got 2 bytes now that are the length prefix is 2 bytes of information, right? So the first one is B8 and the second one is 38. If I turn the hex value 38 into decimal, you see it's the value 56, which is the length, which is the number of bytes that are following, right? So this byte here, 38, is telling us that we have 56 bytes of information following us. And that weird rule which said like take the length of the length is basically saying, okay, the length the length byte is only 1 byte long, so I'm adding just one one plus 1 to B7, which was the last value of the previous rule, of rule 3. Okay, so just to hammer this home, just so this rule can make a little bit more sense, I've just added a byte string of length 255, and now we're still in the B8 range, right? Because 255 expressed as a hex is the value FF, so we're still able to encode to express the length in 1 byte of information. Now, if I add one more, 256, B9, right? We've now hit the prefix B9 because now we have 2 bytes which represent the 256 bytes. We needed 2 bytes to express the hex representation of 256. So this is also why there's such a small range. There's only 8 bytes of information in the range of this rule. The reason is because to get to the next byte, I actually have to get to FFFF, which is 255, which is 255 times 255, right? Whoop, what happened there? Never mind. Okay, so there we go. B9, this was the previous one was B9. Now we're at BA, which is equal to B10. 3 bytes of information to express how many bytes we have. We have 65,000 bytes, right? We'll take it one more further, and just so you can see, like, where are we at? See how long that took to encode? BB, right? That's 4 bytes of information now. So BB is B7 plus 4, which is 11, and 11 in hex is expressed as the hex value B. Like that's what 16,777,171 bytes. So basically, if you get to something which is RLP encoded on as data on the blockchain that has like BB as like the initial byte, well, that's probably like a whale that's decided to upload his biography or something and doesn't care about like the insane gas cost that would cost. So by the way, man, if anyone is still interested and is lost, like just voice it at this point, like because it's only gonna get more complicated.
You still got a good crowd, man, and you're getting some love in the chat, so you're good, I think.
Okay, good. All right, I hope so. I hope you guys have followed me. All right, so rule 5. Now we're in array territory. Okay, now we're in a array territory. So we're like, or list territory as RLP calls it. Okay, so I'm gonna just jump right into it. I'm gonna encode an empty array just so you can see what it is. C0. Okay, C0. Actually, funnily enough, I miscalculated this. In a way, this value C0 is a little bit like 80 because it's an empty value, and it will always just be expressed by C0. So this is the first time that we're gonna see the recursive in recursive length prefix, right? So I'm gonna encode the array with the value OXFF in it. Okay. So this is where it gets recursive. The outer array, okay, is C2, which means that since we know we start from C0, there's 2 bytes in it. And then the first byte is 81. So the parser, whatever's decoding, knows, okay, now I've hit a byte string. And the byte string is only 1 byte long, and it's the value FF. So this is where we're getting into the concept of recursive. So let's try an even more nested value, right? Like an array within an array. See what that looks like. C5, okay? C5. And then so we linearly go through C5. Okay, so I have an array of 5 bytes that we can see over here, and then we come to the first item in our array. 81. Okay, cool. So basically our byte string is only 1 byte. It's above the ASCII range. So and it's FF. And then C2. We've hit C2. We've hit like the next we've hit the next array within the array. The array within the array. And in here we know that there's one byte. Its value is the hex prefix is 81, meaning there's 1 byte after it. Okay, I think you're getting the idea. So I'll just show you one. I'll just show you one more. Okay, and like C8, you can see in here this buffer, this RLP is like nested inside it. It's the exact same one. And then the outer list, the outer array, is now encoding everything else inside it. Okay, so there we go. That's recursive length prefix. They're like you prefix information with bytes that explain the length of the information, and you do it recursively over lists. Okay, so one last thing. We said like this is the rule 5 follows the same rule as the list one. It's from 0 to 55 bytes. So what happens if I encode a byte string of 55 bytes that's within an array, right? So we've hit F8. F8 is outside of the range of rule 5. Rule 5 goes up to F7. And the reason for that is because the byte string required more than 55 bytes to express with its own hex prefix encoding. So the array is no longer in the 55 byte range. So it pushes it into rule 6. We're almost done. We're done with RLP encoding. and we're gonna leave it for a while, and we will come back to it. We'll come back to it, but it's basically, you know, at this point, if you've been following along, it's the same as the greater than 55 rule for byte strings, right? So basically, we just did 55. I'll show you 255, right? We're now in F9, the second hex prefix value after F9, okay? And everything inside it is it follows the same rule. Like this is I've confused myself. Okay, if you were following a lot, like you will, if you want to mess with this stuff, you are going to have to just kind of play with it yourself. But if you were following along with rule 4, you know that like there's extra bytes. In this case, F9, so it's only 1 byte, and this 1 byte then describes further information. Right now, I've talked myself into like a circle, and I can't. Usually, I'm quite good at this point. I'm quite good at sort of like reading the RLP formatted stuff. This time around, like I can't, but I'm not even gonna try it at this point. I'm gonna move on, like because we spent a lot of time on RLP encoding, and I know it's almost autistic, but generally speaking, those 6 rules, they are actually simple, and like what they basically, just to hammer it home, the whole idea is to be able to express nested structures in a linear string of bytes, that when something consumes that information and tries to encode it, it can go through it linearly and say, oh, I'm at F9. F9 is part of the rule of the rule 6, is part of rule 6. So I know that what I'm dealing with is an array of information that's bigger than 55 bytes. Then it moves on and it takes the next piece of and it knows, because it's F9, it knows that it can calculate how far it is from the first value and say, okay, there's 1 byte of information after me that explains how long the rest of the information is. In fact, now that I think about it, I got thrown off by this F8, which is wrong. It's F7. So for F9 means there's 2 bytes of information that represent the length, and now it's starting to make sense. What was it that it's 256? It 100 in hex is the value 200 is the value 255. The reason is the value is 101 is because internally the byte string also has its own hex prefixing. We're done. We're done with RLP. Congratulations if you made it through to this part, because that stuff was painful to even say rather than just explain. All right, so more theory. We're gonna come back. This is all gonna be. This is the like basically just one last thing about RLP. Like it effectively. You can think of it as like the grammar of data on the Ethereum blockchain. Everything in some way or another gets turned into to RLP content. Okay, so all right, we're done. Thank God. Well, let's move on to the next wait, hold on a sec. Let me just make sure I didn't. Okay, is it? Can I just switch then? Okay. All right. So now we're moving on to Radix trees. Things are gonna get a little bit less, you know, just kind of just looking at byte numbers and stuff like that. But is it like I'm gonna wait? Hold on. Let me come back into the chat real quick. Is there anyone like at this point before we move on to RLP? Like, did people understand like the general idea of those rules? I hope so. But like generally speaking, you have to play with it to fully grok it. Like I've actually got to a point now where I can kind of look at some RLP stuff and I can decipher what it is. But the only way that you can really do that is by playing with it, basically.
If you want to see the chat, dude, you see in the top right of your screen, there's a little notification.
Top right.
You see the little chat.
Oh, just
You see the little where it says developer's voice. There's a little there you go. Click that.
This is great. Thank you, man. And yeah, congratulations for getting through all that sort of byte data. But anyone like any questions? Does anyone have any questions? Like, is anyone feel free to ask it while we're here, because actually we have a lot of information to go through still. Sorry, I understood that there are rules to encode the input depending on the length of inputs of bytes. Yeah, that yes, it is the like exactly that. Like it's basically the prefix, like the whole that kind of those weird bytes that we add as a prefix are information to let the parser know how many bytes are part of that item, in quotation item, whether it's a list, and there's different hex prefixes depending on whether it's depending on what it is. So this is correct. We just need to play with it. Yes, absolutely. You definitely need to play with it to get your hands on it. But the rules, hopefully, like I helped you. I will have helped you kind of understand, especially that rule about like taking the length of the length, right? And anyway, you can always come into that repo, play everything back, and just toy with it. All the little code examples that I left in there, all the little things that you can paste into Node.js or however you do it, they're all kind of like interesting values that you can use to kind of like look at stuff. All right, done. Let's go to raid. Let's go to tries basically. Okay, let's. Okay, tries. Okay, really quickly, a trie is an ordered data structure. The name trie or tree, I'm not sure how you're supposed to actually pronounce it, is derived from the word retrieve. It's like it's these four letters inside retrieve. And as the word suggests, is a programming structure that is used to locate data. A trie storage structures. Let's just leave it at that. Like I'll through the rest of the information. And actually, there's loads of really good articles about tries on like on Medium, and I like all these diagrams I've actually taken from those articles, and I'll link to them. I'll put them in the repo. I haven't actually done that yet, but like this is an example. Like by the way, we're talking about like a basic trie. We're gonna build up. We're gonna kind of talk about basic tries. Then we're gonna talk about Patricia tries, and then we're gonna talk about like uh, the modified Merkle Patricia trie that is used in Ethereum. I think this is gonna be more interesting than the RLP stuff. But this is basically the this diagram is a nice diagram that really kind of visualizes what it means by being a data structure that is supposed to be about locating data. Okay, and like and basically like it's a good diagram, but it leaves a lot to the imagination. Like it doesn't really make sense like how what these things are connected. Why is there like a letter on the end of each sort of like arrow and all that kind of stuff. But the general takeaway from these type of diagrams is that information is kind of structured in a certain way that it branches off right when when it doesn't have common data. Here we have like the word word. You can see the word word and the word would, right? They have common data, which is the word, which is the letter W and the letter O. Like there's also these weird little kind of escape zeros at the end. And this basically represents the idea of like a terminator. You've reached the end of like of what you're searching, and at the end there's a value. Okay, like another you might come across like this diagram, which is like the same diagram basically. It's just it's fancier, and it's trying to tell you that it's possible that at each individual letter you can actually store a value. Okay, so yeah, these diagrams are nice, but let's kind of like let's look at it in code so that it can start to make sense in code. Okay, this is this is like a oh yeah. Okay, one thing about the branches, guys. If you want to go through, if like I don't know, if you follow through on like a recorded version of this talk, or if you're looking through it, just remember like each individual commit from here on out is like it starts on the first commit and moves up to the latest commit. Okay? So there we go. Are we yes. No, sorry. Wait, there we go. Okay, so this is like a code implementation of like this try structure. Okay, like you can come in. This is on the first commit. If you really want to go through and see what everything's doing, like it's commented to hell, so you can do that. But I'm just gonna tell you really quickly what's going on here. Like to bring you back to that concept of recursion. Like if you remember that first recursive function that like spat out that object that had all the childs in it. This is very similar. It's gonna basically it's a try it's a it like effectively this is our try node. Okay, it has a special property called 16. Okay, which is the kind of the equivalent of this value over here, which is basically saying that this is where it ends, and for now we're hardwiring a value into it. Okay, we're just hardwiring the value in. Little Easter egg: if someone can figure out why I use the value 16, you'd have to go do some reading. Like, and you show up to the second, if you brave enough after this kind of how this like all this stuff to come to the second workshop, and you figure it out, we're like, I'm gonna think of a prize to give you. So basically, so yeah, so it has that same kind of concept of a terminator, which is expressed by this property called 16. We have a method called put, okay, that accepts a path. We're not going to call this path for very long. We're going to change it to key later on. But for the time being, while we're talking about a word, we're going to think of it as a path. And what this function does is it again in this recursive fashion, it's going to basically it's going to disassemble the path letter by letter, character by character. It's going to create a property on this instance of the try node, right? So path key over here, it's like the first letter of the character. It's gonna stick it on a property, and it's gonna then instantiate a new node recursively, right? And if there's more path left without that key, it's gonna pass it to the put of that, and it's gonna do that recursively, right? And it's gonna build up one of those sort of nested structures. And we also have like the find function, which will do the which is gonna use this same sort of like recursive concept to find whether a path has like one of those 16 terminators, so it can tell us if it exists in the path or not. Okay, so you can come back to this to the first commit. It's called the commit is called Introduction to Radix Trie, and you can kind of look through this yourself. I'm just gonna quickly run it. I don't need this one anymore. Okay, I'm just gonna quickly run this. npm npm run RDX. All right, so basically down like a little bit lower down, I just set up like a little test. I've put, by the way, sorry, I've put the word and the word would as is in this specific diagram. Okay, so like using the find path function. I'm just checking to see what's in the tree. Okay, so exist in the tree word. Like basically, you can see found the word word, found the word would. The word woo doesn't exist in the tree. The word hide doesn't exist in the tree. So you know this code works. Okay, so like basically, all right. So moving on to like building this up, and like things are gonna start feeling more Ethereum like as from now on. I hope. Switch to commit. Whoop. Introduction to rate. Sorry, switch to this commit. Uh, back to the index file. Okay. So now so basically now this is the same code. This is the same code. It's just now for the first time we're gonna add the same words, word and wood, right? The difference now is we're slowly starting to we're introducing the concept of an external database, right? So in this case, it's like a fake database. All I'm gonna do is I'm gonna print the try data to a JSON file, and we're gonna see what that looks like. Okay. Okay. So first of all, now this is in JavaScript instances. This is what our tree looks like. You can see like the property W, the node that has the property O. This node over here has an R and an O. So basically it's the equivalent of this node over here that branches off. Okay. And really quickly, just looking at like our database, this is what it looks like. So this is the nested code implementation of what something like this looks like. And you can see like you got like WO, then it branches off to RD, OD. You've got this special kind of terminating value, and then you have the actual value. So all right, enough of that. Size test. Why? So now just to kind of talk about why these radix trees. What like why even use them? So don't save. Uh, back to index. All right. Okay. Getting more complicated. Like we're moving towards something, right? We're moving towards something. So now, first of all, like our try node class has become it's been modified. First of all, the like specifically like just we need to we need to kind of go through this a bit now. The like what the modifications are. First of all, instead of having that kind of terminator, we're adding a value. We have a property which is a value. So now our put accepts a key instead of a path, and a value. We're from now on we're gonna be using like Ethereum like values, right? So this is the type of stuff that you'll see on Ethereum: strings of data expressed as hex values. Okay, so and the keys that we're gonna be splicing off, they're nibbles, right? And those nibbles, what's gonna happen is instead of placing them on their own individual property, what we're gonna do is we're gonna collect them into an array. We're gonna collect them into an array called branches, and we're gonna place that nibble we're gonna convert the nibble into its decimal format, and we're gonna place it into that index on the branch. Okay, everything else is more or less the same, but just and you'll see is how that prints out. Okay, you'll see how that prints out. So and on top of that, like there's an extra function over here that's just gonna create random entries into the database. And just as a comparison, now we're gonna create like what's effectively like a linear database, which is basically whatever comes out of this. This is gonna produce an array of information that's a key value pair. We're gonna print out out into an array, and we're also gonna take all that information and we're gonna stuff it into the try with the put method. Okay, so I'm just gonna quickly run that. Okay, this is the kind of signature of our try node. Okay, like this is gonna become more this is gonna the reason I showed you this now is because as we move into ethereumjs's library, this is how we're gonna start looking at things. So basically it's the same idea, but that the nibble is like expressed as the position in the index. So we've got 0, 1, 2, 3, 4. So we know that one of the key values that was a bunch of like hex values starts with 4. In fact, actually, in the code, I printed out printed out the tree before like I stuffed in all these random values. So it's actually at this point the only values that are in it are these two put values, and you can see it's like it starts with the value f, and they start and the nibble f and the nibble 4.
Andreas,
see that, yes,
Eddie's asked a question. Says like a hash map / dictionary. You see it on the. There you
go. Like a hash map. You know what? Actually you've actually jumped ahead. Like the ethereumjs implementation of the tree is actually a lot like a hash map or a dictionary. But no, this isn't. This actually isn't like a dictionary. What's more like the dictionary in this example is going to be the linear database. I'm going to print it out for you now so that you can see so that you can see it. So basically, just to kind of try to like squeeze this into your brain, that inside these branches, the first nibble is represented by the what the decimal position is inside this branches array, like what index it's in. Okay, so man, let's just look at the two databases real quick. So this effectively, I think, I maybe I'm wrong, but maybe Eddie, maybe this is what you would have more traditionally thought like a dictionary looked like, right? Like a key value pair. So like just a traditional key value pair. You got a key, you got a value, okay, and it's actually very human readable, and it's like really small in size. Check out our try JSON now, okay. Not human readable, right? Like it's just a mess. In fact, you can't like it's just it's just crazy. Like wait, hold on a sec. Like you can't even figure out what the keys are anymore because they're represented by their position inside that branch, like the index, like completely like unreadable, like to a human. And more so if you look at like if I show you the file size, the linear, more dictionary like database, it's only 21 bytes. The try is 36 kilobytes. So it's even bigger. It's like it's not even memory efficient, right? So it doesn't, at the moment, it's not even looking like a good choice. Let me just close those real quick. So where are we at? Okay, so next, so go ahead.
As I said, okay, yeah, Eddie just said, cool. Yeah, that made sense.
Okay, awesome. So all right, so next branch, and then we're finished with this section, and we can we'll get to the next one. Back to index. Okay, so basically nothing has changed in this code now. It's the same. It's that same sort of like branch based sort of node, right? The only difference is we're not gonna put anything into a database. We're just gonna run a speed test. We're gonna search through. We're gonna look for a random entry in the database, and we're gonna run it 10,000 times each. Okay, so we'll just jump to that so that we could just get to it immediately. Okay. Speed test 1. Using 20 items in the database, linear took 2 milliseconds. Try took 3, so linear is still winning. But look what happens. Look what happens when you add 100,000 items to the database. Processing, 100,000 items in. 2,396 milliseconds by the linear search. The try 3 milliseconds. It literally didn't change at all. It found it in the same amount of time. So that basically is like the power of like these try structures. That's kind of why they're used. They're like this insanely efficient search pattern. Okay, we went on a crazy side just to talk about just that stuff, but like I think actually no, a little bit more because we're building up the information. So okay, so that was that you saw how like memory inefficient you saw how memory inefficient that was. Like there's been different sort of like clever implementations of tries which have tried to combat that. One is what is called the Patricia trie. Well, I'm not going to show it to you at all in code. I'm just going to show it to you over here. Like you can see that it's still the example. Well, it's still the example of word and would, but what it's basically doing is it's cleverly saying, it's like internally it's looking, it's saying, is anything branching off the letter O? If no, or the letter W. If not, I'm just gonna stick things together. I'm gonna crunch. I'm gonna create shortcuts. Okay, and by creating shortcuts, you can see just in this visual diagram, you can see how this one is so dense in information, and this one is so short. It's the same amount of information, but it's like it's expressed in smaller things. And specifically, and like in Ethereum, this node up here, which has like a shortcut, but that doesn't have like a final value, is called an extension node. This node underneath, which has a value and also has like one of these little shortcuts, is called the leaf node. The other one that we've been looking at all this time is the branch node. That one doesn't change much. Okay, so now from here on out, as we start looking at the real Ethereum.js trie library, we're gonna have three types of nodes. We're gonna have an extension node, a branch node, and a leaf node. And the leaf node and the extension node are gonna provide us with like ways to shortcut information when we when we don't need that information. So here we this here, if you look around the internet and you start looking for Merkle Patricia trees, this is considered like the best diagram that describes the Merkle Patricia tree. It really is good, but it's kind of hard to understand just by looking at this one diagram. And I'll explain it to you like now as we go along. But basically, you can see here now we have like an extension node. There's something called a prefix here, which is hex prefixing. It's very simple, and I'll show it to you just in one commit. Here you can see the shared nibbles. This is the idea of that shortcut. It connects to a branch node. The branch node does what like we were describing in the code before, like it sticks a leaf node in the position in the index of 1, F7. Then the leaf node has like its own little shortcut of information because nothing else is sharing it. By the way, this information in this diagram is expressed up here. These are the keys that are being used to create this structure over here. And you can see, like, if you look at it, like you can see, like all of them share an A7. So because they all share an A7, that's an extension node with the A7 shortcut. After that, everything kind of has something different. Or so there's a branch node underneath it. Then after that, there's like nothing shares the 1355. So there's a leaf node that shortcuts that information. And so on and so forth. So I hope this is kind of like you're starting to see this kind of branching mechanism. Quickly, just because it's kind of pertinent to this to the modified Merkle Patricia tree, which we're gonna see now, and that like now everything's gonna start coming together. It also incorporates like a Merkle tree, so things get hashed. This information gets hashed. Like this diagram doesn't make it clear how it gets hashed. I'll show it to you in code how this information gets hashed. But just as a really quick like primer review on like Merkle trees, like Merkle trees are just basically like lots of information that get hashed iteratively upwards, so that you can basically you can be assured that this data is part of the overall set. And like Merkle proofs is the idea that given one piece of data, you don't need all the hashes to prove the top root. Like you only need a select amount of the hashed information to be able to sort of like quickly bounce up and hash everything to prove that it's part of the original set. Okay, so okay, that was it. Section 2 down. The last section to go, and now all this information is gonna come together. So switch to branch. Did I change it? Okay, hold on. Check out Radix. Oh, sorry. Okay. Oh, no, I don't want to save anything. Oh, man, hold on a sec, guys. Force. Okay. So, okay. Now we're gonna start sticking all this stuff together, and now we're gonna start kind of talking in terms of like a full node, like an Ethereum full node. So, okay. So no longer working with custom tries. Now we're gonna actually use the ethereumjs try library, okay, which is like a much more sophisticated. It has like a lot of bells and whistles, and it also internally incorporates like all that kind of information I was telling you about the extension nodes and the leaf nodes and the branch nodes. It's all kind of built into it. So is like the Merkelizing bit, okay. So first off, like just to add to explain to say to Eddie how I said that this is more like a mapping, like a like a dictionary or like a map in JavaScript. Is now we have the ability to directly add byte information into the key and value, right? So now we're starting to get into like real kind of like Ethereum like data. It's no longer strings, it's just raw byte information. Okay, so we're gonna be so in the key we're gonna be working with the byte, like like I'm sure you know what this looks like, but I'm just gonna quickly just show it to you. Oh, so we're gonna be adding the buffer A B C D. Okay, let me just close that real quick. uh and we're gonna be adding the value O1 as a buffer in the value. Okay, so basically now like the put, the get, they're all part of this library, right? Like they follow the same format. We're gonna start looking at like this new method. It's called lookup node, and let's just go through like there's this new property called the try root. Okay, and I'm gonna run this. Uh, so we can talk about like that the output. Okay, so first off, like now we have this thing called the try root, right? And this is part of the Merkle part. We've got a hashback. It's provided. We've inputted one element into our try, and it's created a leaf node, okay? And like you can already see, like the information that we put in was A, B, C, D, and because that's all the information in, it just shortcutted it immediately. Okay, now we're back to looking at decimals, right? The nibbles are 10, 11, 12, 13, which in hex are A, B, C, D. Okay, and you got the value over there, and like specifically in the library, we're dealing with a leaf node. Okay, so you can see that it's a leaf node over here. So let's move on. Let's like move up. Okay, we're gonna talk about hex prefixing a bit now as well. Uh, So what's changed now? What's changed? We're doing the same thing. We're gonna add the same buffer information, the ABCD. We're gonna add the same one. Everything's the same. Like we're doing everything the same. But now, basically, this lookup node, which I'm gonna explain to you a little bit more in detail in a little bit, it's kind of using the root, and I'm going to explain to you why it's using the root, this root hash, to find what this to find what the node is, right? What the node, this leaf node, what it is. But these leaf nodes now have like these new methods. They have this method called raw, and they have this method called serialize. Okay, so we're gonna print out those two methods as it's the same thing that we did before. We're just gonna check these two methods as we do it. So, all right, so there we go. We have the hash. We've got a leaf expressed as a JavaScript object, object, and now we have raw. Okay, like raw really quickly. Now I'm gonna pull you away very quickly because we've got this 20 over here. This is part of the hex prefix. Hex prefix is much easier than RLP, but I gotta just like jump away and I've got to show you what that is real quick. Okay, so I'm gonna read to you what the rules for hex prefixing is. An internal encoding system used by Ethereum Merkle Patricia trees to differentiate between nodes of type extension, branch, and leaf. It is similar to RLP in that it prefixes data, right? So it sticks data in front. And there's only 4 rules. If a node is an extension node whose nibble shortcut, you know, like these values over here, this nibble shortcut. If the nibble shortcut is an even number, we prefix it with the value 0, 0, right? So if it was like ABCD, it would turn to 0, 0, ABCD. If the extension node had an odd number of nibbles, right, ABC, you would only prefix it with 1, just so that you can pad out the byte, so that it could. You don't need the 0, because we're just trying to keep byte information, even numbers. So you just stick the 1 in front of it. If it's a leaf node, again, even ABCD. If it was a leaf node, you'd add the 20 in front, which is what we saw. And if it's a leaf node with an odd number of nibbles in the shortcut, you add the 3 in front of it so that you can pad out the value. Those are the rules. Branch nodes don't get anything. It's just like 0 and 1 refer to extension, and they differentiate whether the information is even or odd. And 2 and 3 does the same for the leaf node. Okay, that was it. That was hex prefixing. So the raw method on the node, it applies the hex prefixing for us, right? So it just says, it kind of creates the buffers, and it says, I'm a leaf node. These are the nibbles that I've shortcutted, and this is the value. Okay. Serialize takes it a step further, and what it does is it takes the raw representation, and it now RLP encodes it, right? So now we're back to seeing RLP encoding for the first time after after all this time. So you can see, like, I won't bother you now with kind of like going through it visually, but like I'll quickly show it to you, right? Like I'll quickly decode, I'll RLP decode the serialized version, and you'll see, like, it spat out the decoded version was that raw format. Okay. And one last thing, like, if let me just encode this. So the RLP encoded raw format, which is the same as serialized, like I'll just quickly, I'll replace that, right? It's node serialized, which is the equivalent of the raw data RLP encoded. If I hash it, okay, if I hash it, whoa, did I console log it? Yeah, I did. I didn't save it. All right, hold on, so that I don't. So I'll just encode the raw format. If I hash that, there you go. Like this, you see that hash? It's the same one. It's the same one that is on our root. It's the same one. So basically, in this, if you go off and kind of like try to look at this stuff, when it says like all this information is hashed, this is how it's hashed. It's basically, it literally takes the RLP, it takes the RLP version, the RLP encoded version of the hex prefix raw format of the individual node, and that's what these prefixes mean in here. So this is the 0. You can see the 2 for the leaf, 3 for an odd leaf, and all that kind of stuff. This information over here plus its value gets hashed. In this case, it's just one. It's just one leaf node. All right. So quickly, all right, moving on. Trying to, because I know we've hit time now, and like I just want to quickly try to get to the rest of this information. Unless people are like, I've had enough, and I just want to like I'd rather do this in like the second one. But we actually, I would, if since you've hung on for this long, I would say stay along just for a little bit more, because we like this is where things are gonna really start getting interesting.
I think you're good, man. Keep going, keep going. This is good stuff.
All right. Let me just quickly just fix this. Okay. Where are we? All right. Introduction to LevelDB. All right. So now we've gone through all this kind of like mind bending information. Like we're finally now starting to see it. We're coming back to like seeing Ethereum structures. Okay. So basically, like Ethereum is backed by databases, right? So basically, like it's just normal databases that like LevelDB databases or RocksDB databases that just kind of have like all this information in it. And but like what happens is that you like what is necessary is for that information to first kind of go through this trie interface to get all the information sort of like hex prefixed, RLP encoded, so that it can then be put into the database. Okay, and basically right now what I've done is I've included the LevelDB database, and I'm initiating the tree with the database, and you'll see what that means. Like again, we're just adding the ABCD with the value, just that leaf node. We're gonna look at the serialized version of the node. We'll look at the we'll look at the serialized version, and we're gonna look at the hash, which is also the root of our node because there's only one element in it. And on top of that, we're gonna iterate through our database, and we're gonna look at what the values are in the database. All right. So all right, boom, there we go. Serialized version. There it is. It's the RLP encoded array with the 3 bytes for the first item, the second byte that doesn't need RLP encoding because it's kind of in that 0 to 127 range. Okay, all this information over here got hashed to create this data, and then in the database, the key is the hash, and the information is like that RLP encoded value. Okay, so the database takes this stuff that we just kind of mashed up from the tree and stuffs it into a database that is which is on a full node. Okay, so let's like we're really close, guys. We're getting there. So we're now gonna look at the same thing. We're gonna it's the exact same code with the serialized, the hashing of the serialized, looking through the database. But for the first time now, we're gonna put a second object. Okay, we're gonna put a second values, the buffer BB and the value 2. Okay, so let's go. All right. So now if you notice the first nibble, A and B are different. So immediately the first kind of the top, the root of the branch of our tribe becomes a branch. And I won't waste time counting them, but you can trust me, they're at position 10 and 11, which represent the nibble A and the nibble B. And then inside, if you look, since we've got the hex prefixing, like I'm kind of used to looking at it, like I can tell this is a leaf node, and because it's 3, it's got 3 nibbles that it's shortcutting, then the value. The other one has 1 nibble it's shortcutting, so it has the value 3 and then the value 2. Okay, so now this structure over here now completely describes the trie. When you serialize it and you stick it in all the RLP encoding, this is what you get now. Okay, and like this whole RLP structure, and this is why RLP was a useful part in this kind of like recursive format, is because this whole string now, it describes the whole tree at the moment with 3 elements in it. You can see it's an array of D7, so I know that all this is like a certain number. Then we hit 80, 80, 80. All these are empty values. 80, 80, 80. If you count all these, you'll get to position like 10, which now is an array, which is an array with an item with 2 bytes. The first byte has a 3, so I know this is a leaf. These are the shortcutted values, and this is its value. Then at position 11 in the outside branch, which is kind of like RLP encoded into this format, we've got the second leaf, right? C2. This is an array. It has the only 2 bytes. 3, which means it's a leaf. It has the nibble B, and then the value 2. Why did I even show you this stuff? Okay, why did I go through all this stuff? Well, this is where it all starts coming together. This is, oh man, this is too big to see in one line. But this is now our Ethereum database. Okay, our Ethereum database, it has 2 hashes. Okay, because we did.
Andreas, you got a question, man.
Okay, go. What is C482? Where are we going? Where was it? C482. Okay, so basically, we count. I won't do the math, but if you do the math here, you'll find that the RLP encoding of this is basically the rest of the information. Okay, and this is an array. 80. Every time you see 80, it equates to these empty buffers. Okay, when you count to the 10th position, I know it's 10 just because I know that we've been using A, B, C, D, and BB, right? So I know that it's a position 10. C4, if you go back and you look in the rules of RLP, that's rule 5, which says this is an array of 4 bytes. These 4 bytes are the content of this array. When you hit A2, so we first start looking at the first item in the array. When you see A2, that's an RLP rule. It's rule 3, which is saying any information, like if I have a string of bytes that's more than 1, or just add it to the value 80. So that's 82. So now I know to look at the next 2 bytes. Now, because remember, RLP is agnostic. What is gonna collect all this information? What's gonna try to retrieve this information? Like a Merkle Tree library. So a Merkle Tree library knows internally that if in these structures, if in these RLP structures, it hits a 3, it knows it's looking at a leaf node. Okay, you're just gonna have to trust me on that. Like, I might kind of seem like magic at the moment. Like, what? So every time I see a 3, yeah, every time it sees a 3 within these structures, it knows it's looking at a leaf node. It knows that because there was no 0, 1, or 2, it knows that all this is a branch, and it knows to put this leaf in this position. Okay, and C2 is the next array, which basically this array over here. And C2 says, okay, I have 2 items. I've just got 2 values. 3B, right? 3B here, O2 there. So this whole RLP encoded structure recursively, in a linear fashion, created our trie structure for us. It encoded our trie structure for us. So any library that knows about tries can pick up this RLP value, and it can rebuild the trie. And this is basically, now we're back to kind of like Ethereum proper, right? So basically, imagine this is the database. We have the hash. We have the hash of the RLP data, which encodes the trie information. So when on a block, you go and say you look for the state root, and you say, okay, I've got the state root. If you were to, in whatever way, like, just take my word for it, if you were to look up that state root on an Ethereum Full Node database, it would give you back, like, just stretch your imagination for a bit and imagine that this was like a much, much bigger, much more complex trie structure. It would give you the state of Ethereum at that specific hash. But if you then, because we put two values, right? If I was to put this hash value, it would provide the historic state of the Ethereum of the Ethereum database in its trie format at this time. So this is the first time, like now, this is how you're starting to see that basically this is how the kind of like commit, like GitHub like history is achieved in Ethereum. It's basically by hashing the information about the trees, storing them with their hash, and then when you go back to retrieve a root via like a trie mechanism, you will then collect back like the state of the tree in that format. And then one last commit, and then one last commit and we're done. Oh man, this is a marathon. So
you're a monster, Andreas, mate. You're doing great.
All right, so there we go. I'll take that. I'll take that, man, and I'll draw confidence from it. So basically, like really quickly, I'm doing the same stuff, but now I'm stuffing I'm stuffing 4 values into the trie. I won't take too much time on this. The only thing I want to show you is it's doing the same thing. I'm not even showing you the database, but for the first time now, you're gonna see something weird. No longer are you seeing like these leaves and stuff. You're seeing a hash. And the reason, I'm just going to explain the reason to you. And you can, if you want, you can go through these commits and you can go back. The reason it does, this is an optimization that is done behind the scenes, is that if the RLP encoded information, like, and this is where it happens, like the RLP encoded information of some branch gets beyond 32 bytes, it gets stored in its own key value storage on the database, and it's referenced. It's referenced back. So because like our trie structure now got too complicated, and like so that you don't end up with these massive sort of like RLP strings, it starts breaking it up, and it starts sort of like referencing information from a hash, looking it up on the database, and then rebuilding it in that way. Congratulations for getting all that stuff. If you followed me through it, like well done, because like that was like an insane amount of information. But like what we have done is like we've basically gone through how any information, whether it's like text information, where like any kind of like value info, a transaction, whatever you do, whatever you pass to the Ethereum, to an Ethereum node, it's going to take that stuff, it's going to kind of form it into these trees, it's going to do the hex prefixing, it's going to do the RLP encoding, it's going to hash it, and then it's going to stuff it into the database. And that's how stuff ends up on the database. I'm done. That was it.
Wow, man. That was a lot. I'm very impressed at how you maintained that all the way through. That was super impressive, dude. Well done.
That was a lot of information, and like I imagine people got lost. But like basically, I wanted as far as sort of like a contribution to the DAO. I wanted all that stuff in a video because like I've spent 2 months like looking at this stuff, and I could never find just one source that would explain it all. So like, yeah, I just wanted to contribute that to the DAO so that basically for people, whoever wants to go and find out about this stuff, if they chance upon this, if they've done reading, they can just get all of it sort of like outlined just in one go. So, but for generally for whoever, if anyone was like, okay, this was interesting, like if you come to the next workshop, we're actually gonna apply this stuff. We won't go through this much theory or anything. We're just gonna literally like apply it to the transaction tree. We're gonna apply it to the receipt tree, and we'll also apply it to storage trees, which is actually, for me, it gave me a lot of insight onto things that even then affect solidity. So come if you bear it, come to the second workshop.
Mate, check out the chat.
Let's go. Okay, back in chat. I'm done. So from here on out, we can just talk. By the way, I'll stick around if people are lost. Understood. Well done, man. Well done. I feel more autistic already. Yeah, exactly, man. Trust me. Like this has been like I've been stuck on this stuff for 2 months. I've read half of Medium, trying to understand this stuff. But like I think it's worth it. I think it's worth it, and especially later on with when you get to storage, when you get to contract storage, it gives you some insights. It really does give you some insights about like what storage variables are, what like data packing is, why, for instance, mapping is so weird in like contracts, and how you can't iterate over it. Like this information will be nicely applied. All right, let's see. That's amount of information you're presenting here. Thank you very much. No problem, man. Thank you for sticking around the whole way through. So I guess 16 as the terminator in the first try implementation was because that's one more of the max. Man, I give you points for that. Isn't the right answer. There's a technical answer, and you'd have to dig it up in some Medium articles, and I'll post them in the repo. But that isn't the answer. But it was a very insightful comment because and actually it's a hint. It's a hint. You're on the right track with that one. I thought so too. Kind of like null terminator. Yeah, yes. I mean, that you guys were thinking correctly. Cool. Glad you're gonna come to the next one. And you're very welcome, Brian 5. Man, like, by the way, if anyone, I'm like that was just. I feel relieved to finish that.
I was gonna say, mate, like, what is it? How does it feel like holding like that much in your head and speaking through it in like one, like almost like one breath? Like, it was super impressive, dude.
Man, well, I mean, it's taken a hell of a lot of preparation. Let me tell you that. Like doing it really, like, for me. I mean, I've gone super autistic. You can show me RLP strings, and I can decode them for you, like without I don't have to. I can decode them. I can decode them by looking at them.
It's like,
But
you learn like a new language. You're looking at it rather than like thinking in binary, you're thinking in someone else, like completely different.
Yeah, I learned a new language, which will not help me get any dates. Let me tell you that.
Pasky's asked a good question. So this, to me, mate, like, to be totally honest, a lot of it goes is beyond Go on.
Sorry, let me. I'll post it in the chat right now. Where should I just post it in the chat, or?
Yeah, post it in the chat, and then you and I can have a conversation async about how best to write the description for the video or whatever, so people can find what they need.
Yeah, I know Kung Fu. Nice, man. Man, actually, I was thinking, like, I just didn't have time to make slides and all that kind of stuff. I wanted to at the end, I wanted to show like that picture that, when Neo sees like the agents in the Matrix at the end, he kind of sees their silhouettes. I wanted to post that.
That's exactly how I'm imagining your like eyesight now, mate. It's like you see characters and it just becomes like reality.
Well, I'm gonna be happy to step away from it for a bit now. But like workshop 2 will be even more practical. Like, I know that was just like, I don't know, it was autistic stuff, but like it will be practical. Like, it will be stuff that will help with development. Like, we'll kind of talk about things as light clients, giant tree. Yeah, basically. We'll kind of understand like what a light client is doing. Why doesn't it need all the data? Basically, because it can kind of prove it can collect data from the database. It can ask for data, and then it can check it. It can check whether it kind of it follows up to the root and all that kind of stuff. So yeah, the next one's not gonna be so intense.
Nice. So in summary, what is the next one about? Like, where do you take it next?
So basically, like, we are going, like, all this stuff that we've been talking about, like the Merkle trees. We will look at the Merkle library in more. There's some other really interesting functions on it and stuff. We like the ethereumjs try library. It has like all these other bells and whistles. We'll look at those. We're gonna talk about one more aspect about sort of like how things are added to storage, which we didn't talk about now, and then we're gonna implement that stuff on proving an actual transaction, a set of transactions in a block. We're gonna prove that they're authentic, We're gonna do the same for receipts, and we're gonna prove we're gonna do the same for the storage root of a contract. So basically, we're gonna deploy a contract with a bunch of variables in it. We're gonna edit the variables, and we're gonna see how they are stored in the database and how it creates a storage root.
Nice, man.
Yeah.
Yes, very, very, very strong performance. Sondam's asking if there's any like of the research that you've got, if there's a way that you can maybe gather that and share it somewhere so folks can, I guess, go down the same rabbit hole.
Yeah, 100%. I'm gonna put all that stuff in the repo. I just didn't have time. I'm gonna update the repo with like a list of all the different articles so you can read through them.
Amazing, dude. I think this could be a really good reference resource for people. Like, I haven't gone anywhere near this rabbit hole yet, but like I could still follow along, and I can't imagine how challenging it must be to piece that stuff together. So I think what you've done here is huge value add for anyone that's interested in learning in this space, mate. So yeah, very, very grateful and super good job.
I appreciate that, man. I robbed you of the pain of figuring it out and kind of knowing it, but please, like come back to the repo and come back to the video if you go over it, if you choose to go over it at some point.
Yeah, for sure, man. So the next workshop is same time next week, is that right?
Same back time, same back channel. We'll be doing it next Wednesday this time.
Awesome.
And it'll be shorter. I know we went over.
It's cool, man. Don't worry. I think there was so much value in there that, like, however long that was going to take, it was definitely worth it, right? And you obviously had a structure and format you wanted to follow. So I don't think anyone here minds at all, mate. I think you've done a super good job.
Okay. I appreciate that. Appreciate it.
You're welcome. Ropats, I think, opened up a thread for any async discussion. Ropats, do you want to just at that thread, like if you do a hashtag in the chat and then reference the name of the thread, assuming you're still with us. Let me see if I can find it. Where were we talking, Andreas? It was in the workshops channel, right? Yeah, here we go. I got it. Join thread.
Yeah, that's the one. That was it. That's the one I wanted to end on.
Nice.
Good job.
Yeah, mate, and like as you like as this content evolves, like whatever you need us to do to make it more discoverable or whatever, like just let us know, and we can try and make sure that you get it when you get it exactly where you want it, with all the reference material, that it's all tagged up correctly so people can kind of find the information that you've brought together for them.
Yeah, I'll be updating it with like the reference information like within the next couple of days, and then like I'll update some more branches. By the way, guys, at the moment, and gals, you have to download the individual branches. Like there's the master branch just has the introduction, and the branches are the RLP, Radix Trie, and Merkle Patricia trees are individual branches that you need to pull at the moment. When it's all said and done, I'll put it all together in master as well, so it all just sits in master. But for the time being, just like pull the individual branches as well.
Sweet, dude. Super good job. I imagine you're probably thirsty now.
Oh man, I'm gonna go have another cigarette and I'm gonna crack a bottle of wine. All right, guys. That was I don't know if I call that fun, but thank you for sticking around throughout the whole thing.
Yeah, really, really good job, man. I will hit you up in the DMs after, and then we can figure out how to get that information once you've gathered it into the description for the video and stuff. But yeah, amazing job, mate. I can't wait for next week. Well done.
Nice one, guys. All right, thank you for coming.
See you, dude.
All right, see you guys around. Bye.
Bye.